Hello everyone, my name is Anggit Raksajati. In this video, I'm going to present you overview of Introduction to Chemical Process Design. So one of the role of chemical engineers is to design a system, for example, a chemical plant that are beneficial to mankind and also it has to be economical. Design is a complex and varied activity requiring expression of creativity in discovering what, why, and how new things should be devised. Idea for chemical processes can come from anywhere. For example, sales team discover a customer need for a material with properties not covered by any product currently on the market. Or you can find a new catalyst that can dramatically reduce manufacturing costs for a chemical produced by a competitor. Your research team could develop a new monomer whose properties look promising for producing a polymer for car bumpers. Or your management asked to discover a process to utilize the surplus products currently produced by the company. So the synthesis activity is the process of converting an abstract description into a more refined description. You have to combine a lot of different disciplines and courses to be able to design a plan effectively. The first two steps are concept generation and generation of alternatives. The concept generation could include the steps of identifying a different concepts on which to base the design. Stick to the chemistry found in the literature, or you can develop your own process through R&D. You may have an option to stay with a well-proven process from a commercial licensor, or you can look for an unconventional process. You can purchase a process package or adopt a particular strategy to solve the design problem. In terms of generating alternatives, you have a lot of options nowadays to find sources, for example, library, corporate files, consultants, or directly to the licensors itself. You can brainstorm to question this alternative and develop new ones. And then the third step will be to analyze each alternative. You have to establish how each alternative performs, and then you carry out the mass and energy balance to find the flows, composition, temperatures, pressure, and the pros and cons of each alternative. That will help you for the next step, which will be to evaluate the process performance, where you have to select the best or the most appropriate technology for your process, what will be the economic work, what will be the operation flexibility in terms of the safety or the HSE concern, etc. And then last, the part will be the optimization in order to get the final configuration for your process. So flowsheet is a diagrammatic representation of the process steps with their interconnections, whereas a simulation is a mathematical model of the process which attempts to predict how the process would behave if it was constructed without using direct experiment. For the flowsheet, the most simple flowsheet would look like this. Maybe it's quite similar with a black box concept in the heat and material balance course, where you have your main feed streams, feed 1, feed 2, feed 3, and so on. And then you have a black box, whatever process required in order to convert those feed into your final products. This black box could include some reactors, separation, recycle, feed preparation, heat exchanger network, etc. And then the basic performance criteria of a chemical process design, for example, to select the best technology, it has to be economically feasible. It has to be environmentally friendly, minimize waste generation. Any waste or byproduct must not be environmentally harmful. And then it has to be energy efficient and clean technology or less pollutions. The health and safety has to be in first priority. You have to consider the operability and the flexibility of the process, as well as the availability and the reliability of the process. This is the example of the approach to process design, which is known as an onion model. You have at least 4 layers in this onion model. This is to determine where you have to start when you want to build your design or the plan. You have to start from the inner layer, which is the reactor. So out of all the equipment in your plan, apart from the utilities, you have always to start from your main processes. That's where the reaction is. So what kind of the reactor, what will be the operating condition, what kind of pathway of the reaction, that would be one of the first question that you have to be addressed. After you finish your reactor design, then you have to start thinking about how would you separate your product from the feed. How would you separate your main product from your byproduct? And then if there are some unreacted feed, how would you separate and then recycle it back to the main reactor? And then after you finish your separation, you already get your final product in the required specs, in your required purity. Then you have to think about your third step, which will be to design the heat exchanger network. This is to combine the all hot and cold streams inside of the process that you can match and exchange, so that your outside utilities or the external utilities which will be minimized. In that case, the operating cost will be minimized. After you finish your heat exchanger networks, that's where you have to start thinking about the utilities section. This is the generic structure of a chemical process. From your feed, you will have a reactor feed preparation. For example, maybe you will have some pump, compressor, or heat exchanger to increase the temperature of your feed. And then it goes to the reactor at the desired or at the optimized condition, at the desired pressure and temperature. The reactor, you will have to ask and answer a lot of questions. For example, the type, the operating conditions, the catalyst, the arrangement, and so on. And then when you finish your heat and material balance in the reactor, you know the conversion of the reactor, you will get the composition of your reactor outlet. That's where you start to design your separator. And maybe you will have some separator feed preparation. For example, you have to cool it down in order to separate it using a distillation more effectively. In your distillation design, you will design, for example, what kind of tray or packing would you use, how many stages required, what will be the reflux ratio, what will be the other parameters to be set in this distillation. And then if you have some light unreacted feed, you will have to recycle it in order to make your process and your feed stream more economic. Then you get your final products, and maybe there will be some waste streams which will be sent, for example, to a wastewater treatment before it's being discharged to environment. So this is the generic structure. In general, most of the plan would be able to be designed in such sequence. Of course, there will be some special arrangement for some specific application. In terms of the sequence of the design evolution, again, from the onion model, you have to start from your reaction system. So answer this question: what kind of the reactor type, batch, plug flow reactor, or continuous stir tank reactor? What will be the best or optimized pressure and temperature? And then you have to think about the order of the reaction, the exothermic or endothermic reaction, before you will be able to answer those optimized process conditions. Once you know the best conditions, you will be able to find the equilibrium at those conditions. Then you will be able to solve the heat and material balance. And then using the kinetics data, for example, the order of the reaction, the kinetics factor, the Arrhenius, the activation energy, you will be able to size the reactor in terms of the volume, diameter, length, and so on. And then next sequence, you will have to consider the separation and recycle. This is just an illustration or an example, okay? So in this example, you cool down your reactor so that some of the unreacted feed and some of the products will be condensed using a simple separation. In this case, the unreacted feeds goes to the top, which is a light products, and then being recycled back to the reactor. Meanwhile, the products and the byproducts goes to the bottom of the first separator because it's the heavier components, and then it's sent to the second separation column where you separate the products at the top and the byproduct at the bottom. So this is the second layer in the onion model. You finish the reactor and then you finish the separation and the recycle. Again, you will have to decide what kind of separation method. Maybe distillation, maybe absorption, maybe membrane would be more suitable, filtration, and others. If it includes a solid, then that gets more complicated, but maybe we will have other options that you have to consider. And then again, you have to decide the operating condition of the distillation column. What would be the best pressure at the top, the best pressure at the bottom, and then you will be able to know the feed pressure of those distillation column. Again, the temperature that will be dependent on the purity or the spec of your product. So you will be able to decide the temperature, and then you will be able to evaluate the condenser and the reboiler duty. And then last is the sizing. Again, the number of stages, the diameter, etc. The third step in the design evolution is to elaborate or include the heat integration into the process. This is the third layer in the onion model. So this is the flow sheet at the end of your second sequence. Now you have to apply a pinch principle for heat integration, where you match available cold and hot streams to minimize the utilities required as well as the OPEX. For example, in this case, you have a preheater before the reactor using a heating process, and then you have a cooler after the reactor using a cooling water. This is a standard heat integration process. You can match these two exchangers into one exchanger. In that case, you will be able to minimize the utilities required. For example, the first option, now the feed first preheated using the condenser duty of the distillation column, and then again preheated using the hot product from the reactor. In that case, your steam requirement before the reactor will be much lower. And then after it exits from the reactor, the hot stream is sent to the reboiler of the first distillation column. You take some of the heat, and then it's being cooled again in the internal heat exchanger to heat the preheated feed. And then in that case, you will have a cooler using a cooling water, but at a much lower utility required. This is the first option. Maybe there are second, third option, fourth option, and so on. So that will be the steps that you have to decide at this stage.